Hi friends, welcome to the second video on inverse Laplace transform. In the first video, we saw about some basic formulas. Now, we will see how to convert the Laplace transform of some properties to inverse Laplace transform. The first property we will be seeing is our first shifting property. What do we know about first shifting property? Laplace of e power minus at into f of t is nothing but Laplace of f of t, where the variable s is replaced with s plus a. So whenever we have an exponential function as a product with any other function, exponential function shifts all your s to s plus a in the Laplace of the formula. What will be the inverse of it? The inverse of it, when you have a function of s plus a, then this s plus a will now shrink back to s. Over here, s as expanded to s plus a. S as expanded to s plus a. In the inverse, s plus a will shrink back to s. If it shrinks back to s, it comes outside as e power minus at. Notice if you have plus sign here, you will have minus over here. If you have minus over here, you will have plus over here. And then you will just have Laplace inverse of f of s, for which we know that the value is going to be f of t. Hence, what do we do is whenever we have an expansion of s, shrink it to s by pushing out the exponential and just find the Laplace inverse for the existing function. We will try to apply this to few examples and see how this works. Problem number 1. Let me find what is going to be Laplace inverse of s plus 3 divided by s plus 3 the whole square plus 6 square. Now, usually I know it is something of the format s by s square plus 6 square. But additionally what we have over here is something called as 3, which is present both in the numerator and in the denominator. In which case, what will I try to do is, I will try to shrink this s plus 3 to s. If I shrink this s plus 3 to s, what will happen to my function? This function will now become s plus 3 is replaced as s. This s plus 3 is replaced as s. So you have the whole square. So it is s square. And then you will have 6 square. Now, after shrinking, this plus 3 comes outside as exponential. So, since it is plus 3, it is pushed out as minus 3t. Now, this s plus 3 has been shrinked to s back by pushing the exponential outside. The next step will be e power minus 3t, and now Laplace inverse of s by s square plus 6 square. We know that if it is s, it has to be cos. So this is going to be cos 4t. Hence, this will be my final answer. Sorry, this is going to be cos 6t. Sorry for the error. So since it is 6 square, it is going to be cos 6t. So what does this exponential function do? It expands in your Laplace, but in inverse Laplace, this s plus a will shrink back to s to give you your answer. We will try to apply to few more problems. What will happen to my Laplace inverse of 5 divided by s minus 2 the whole square plus 5 square? Now, instead of s square, I have it as s minus 2. So when I shrink this s minus 2 back to s, what will be left out? I will be having 5 divided by s square plus 5 square. But this shrinking will move this outside as exponential. Since it is minus, you will have positive 2t. Hence, this is nothing but e power 2t, and 5 by s square plus 5 square makes it as sine 5t. Hence, this will be my final answer. Let us consider this problem where I have s divided by s square plus 4s plus 5. Now, as such, the denominator is going to be a quadratic equation. What I can do is, I can convert it into a perfect square by dividing the second term, that is coefficient of s by 2. In which case, I will have it as s plus 2 the whole square. 2 square is going to be 4. So, but you have 5 as a constant. Hence, the extra value is going to be equal to 1. We are making use of the property of converting into perfect square. Now, you can notice that if I want to shrink, then it must be s plus 2 for shrinking. But in the numerator, I have just an s. In order to balance, what do I do is, I add and subtract a 2 in my numerator. In which case, I make this as s plus 2 minus 2 divided by s plus 2 the whole square plus 1. Now, split it into two terms, likely s plus 2 divided by s plus 2 the whole square plus 1 and minus Laplace inverse of 2 divided by s plus 2 the whole square plus 1. Now, I know the process that whenever s is in the expanded format, I can shrink it back. So what do? I shrink s plus 2 to s. How do I shrink it? I pull out e to the power of, since it is plus, that comes out as 2t, leaving you with Laplace inverse of s by s square plus 1 square. Now, over here, this is a mere constant which can be taken outside. So that comes outside as 2 times, and this will be 1 divided by s plus 2. So if this s plus 2 is shrinked back to s, it comes outside as e power minus 2t, leaving you with Laplace inverse of 1 divided by s square plus 1. Now we can compute the final answer for this stage as e power minus 2t. Since it is s, we have it as cos t because the constant is 1 minus 2 e power minus 2t, and since it is a constant, this will be your sine, and the value of the constant is 1, so it will be 1t. So in this case, what we can do is, we can take our e power minus 2t common outside, so that will leave us with cos t minus 2 sin t. Hence you keep in mind, whenever you can factorize your denominator, convert it into a perfect square, and then for the factor, you can just adjust your terms so that they are uniform throughout everywhere, and then you can shrink your factors by flushing out your exponential of the corresponding value and taking Laplace to the left out quantity. So this is going to be how you can apply your first shifting theorem to your inverse functions. Thank you.